Hello, we're going to do one more enolate reaction. This is, I think, kind of the last reaction of enolates that we're going to have to know. It's called the Michael addition, and this gets back to we're going to pull back in conjugation and all that other stuff and react it with enolates and talk about that a little bit. All right, so the Michael addition is the combination of an enolate plus a conjugated carbonyl. So we have talked about the aldol reaction, which is an enolate plus a carbonyl. We've talked about a Claisen addition, which is an enolate plus a carbonyl. Right? Now we're going to do a Michael addition, which is an enolate plus a conjugated carbonyl. So what is that going to look like? So we have an enolate. Hopefully by this point we're pretty familiar with what an enolate looks like. Right? If we have acetophenone, treat it with a base, we're going to remove the hydrogen from the alpha position, right, and make our enolate here. With conjugated carbonyls, so obviously there's going to be a carbonyl present, and then within that carbonyl we're going to have, I don't know, I'm just going to put something over here. Let's make this an ester. Okay. Next to that carbonyl we're going to have, so double bond, carbon-oxygen double bond, we have a single bond here, and then a double bond going this way, and then we can put whatever else we want over here. I'm just going to put an R group. But this system here where we have a double bond connecting the alpha and the beta position of the carbonyl is a conjugated system, right? If we were going back to our kinetic thermodynamic chapter where we talked about this, we have 1, 2, 3, 4. We have 4 atoms, we have 2 pi bonds, and so we can start to think about how does this reaction happen, right? So let's take a moment and just think about what an alpha beta conjugated system is going to react like, right? So we have a conjugated system that looks like this, right? And this doesn't have to be an ester, it can be a ketone, it can be an amide, there's a lot of things it can be, right? So really I should put another R group over here, but we're already into this, so let's see how it goes. Now when we analyzed conjugated systems before, we said, well, we always put the carbocation at, either carbon 2 or carbon 3 and try to figure out where the most stable position is. By having a carbonyl in here, right, the carbonyl means that the most stable position for a carbocation, the most reactive position, right, is always going to be that carbonyl carbon, right? So the most reactive position is the carbonyl carbon. And if we think about that, that shouldn't be a surprise because, right, we've really done a lot of reactions that have happened at carbonyl carbons to this point. And so we know right away that that's going to be the most stable position for a carbocation. It's got the oxygen to stabilize it by resonance. It's got this pi bond over here to stabilize it by resonance, right? This is where we want to think about this. And so we don't have to add acid to make this reactive, right? We can just think of the resonance structure of this where we have cation here, negative charge up here. This is a nice stable resonance structure. We have lots of potential resonance structures. We have the carbonyl, which we have over here, but we also have this resonance structure where we move the pi bond over and make this beta position, right? Remember, this is the alpha position, this is the beta position. We make the beta position into a carbocation. And this is a new reactivity. This we haven't really seen before. But what's important to note here is that the beta position has carbocation characteristics, right? The beta position can react as if it is a carbocation. So if we have a nucleophile around, we can add that nucleophile to the beta position. Now, the good news is we have a nucleophile around, right? We made a nucleophile. The enolate is going to be our nucleophile. And so when we react this nucleophile with our conjugated carbonyl, remake the carbonyl over here, this is going to react at the beta position. Right? And we're going to add electrons to that beta position. And we know that that can happen because this is a conjugated system. And so we know that if carbon 3 in that conjugated system is reactive, carbon 1 will also be reactive. And so we can then move these electrons over right? As the electrons add to the beta position, it kind of pushes these pi electrons out of the way, and we're going to end up breaking the carbon-oxygen pi bond and pushing electrons onto the oxygen. And so what we get out of this now is going to be our conjugated carbonyl is going to end up looking like this, and then our enolate turns into something that looks like this, right? So once again, this is a place where we want to make sure we count carbons. We have 8 carbons in our nucleophile. We've added those 8 carbons right over here. Right? So obviously we've also created an enolate here, and so now we have to do something with this. I'm just going to, in workup, add H+, right? So we're going to add like water to this or whatever. Somewhere in there we're going to add an H+, and so we're just going to remake the carbonyl here and add H+ to that. And so the product that we get out is going to be a compound with 2 carbonyls that end up being kind of far apart. Right? Because we're adding to the beta position, right, we end up with this carbonyl from our enolate being kind of way over here, if this is carbon 1, and then the carbonyl from our conjugated carbonyl being over here on carbon 5. So we get this 1,5 dicarbonyl. Right? Michael additions, the addition of an enolate to a conjugated carbonyl compound will always give you a 1,5 dicarbonyl product.